metric in the conformal class. And in fact, all metrics in the conformal class, theta G is exact or closed.
I'm sorry.
Yes.
Is there a way to make the zoom a little bit closer to the blackboard? It's
yes, somehow the zoom, the automatic zoom stopped. But Andrei, if you can speak louder, I'll be fine.
Okay.
okay, thank you.
Yeah. Through the camera. Yeah. I don't. You can see Adrian from here.
Yes, but it's the zoom moves constantly, so I hope it stays closer to the blackboard.
Yeah.
Okay.
I'm sorry, I don't know how this works. I'm not
Okay,
used
okay.
to such
No worries.
advanced techniques. As you see, I'm old fashioned. I'm not blackboard. Yeah. So you see that being for the lead form being exact or closed does not depend on the metric. Whenever you change the metric, the property remains. And now some remarks. First, if theta G is 0, if the lead form is 0, you see that means that G is parallel. So that this is equivalent to nabla being the Levi-Civita connection of G. Then theta G or nabla, let's say, is exact. Is exact. If and only if it is the Levi-Civita connection of some metric in the conformal class. Because you pick any metric G, and then theta G by assumption is exact, so it can be written here. And then using this transformation formula, you see that nabla is in fact the Levi-Civita connection of the metric with 0 lead form. So we just multiply by d to the minus 1. And the point nabla is closed if and only if it is locally Levi-Civita for metrics, for some locally defined metrics in the conformal. Okay, and now I want to, this is the case which is of interest for us. So let me explain a bit further how you can equivalently describe these closed bistructures. So assume now nabla closed. And let us take G in the conformal class and with the theta G value form of nabla with respect to G. So we go to the universal cover. Take the universal cover and lift everything to M trigger. And we consider G twiddle, which is pi star of G, theta G twiddle, which is pi star of theta G, and nabla twiddle, which is in some sense also the lift of nabla. Now, because this is simply connected, the closed form theta G becomes now exact. This is exact. So, in fact, on the universal cover, on a simply connected manifold, every byte connection is every closed byte connection is exact. So we can write theta g is E of some function phi. And that means from the previous remarks, we get that E to the phi to minus phi g twiddle. If we denote this by, let's denote it by H, then nabla H, the Levi-Civita connection of this metric is nabla twiddle. So by lifting to the universal cover, our closed byte connection becomes exact. So it is the Levi-Civita connection of a metric in the conformal class. And now the thing that we would like to understand is how does the fundamental group which acts on M twiddle, how does it preserve or not preserve the function phi? So we know that phi1 of M preserves every lift. So in particular, theta twiddle. So if we have for every gamma in the fundamental group, we have gamma star theta twiddle, it is theta twiddle, and we have gamma star of d phi is d phi. So that means that d of gamma star phi minus phi is 0. So that means that gamma star phi is phi plus a constant, plus some constant which depends on gamma. That means that phi star of M, phi1 of M, sorry, acts by homotopes with respect to H. Of course, phi1 of M preserves the lift of the metric downstairs, but it only preserves H up to a constant because you have gamma star H by the formula here is just e to the minus c gamma H. So that's what I call a homotopy. It's when I pull back a metric, I multiply it by a constant. Of course, in particular, this shows that if this function phi is not preserved by phi1, which means if there is at least one constant c gamma which is non-zero, then we have strict homotheties. In particular, H is not complete. If in fact theta is not exact. Okay. And now the idea is that conversely, whenever you have such a situation, you have a closed byte structure on the manifold downstairs. So conversely, if you have on the universal cover of M, you have a Riemannian metric H, such that phi1 of M acts by H homotheties, then we cannot project then on M, which is M twiddle modulo by 1. We cannot project the metric H, but we can project nabla H, because every homotopy preserves a homotopy of a metric preserves the Levi-Civita connection of the metric, so it can be projected, and but not H. And this is so the projection of nabla H will be our closed by connection, not H singular. So I just I hope I made somewhat clear that the correspondence between closed by connections on let's say compact manifold and co-compact groups of discrete groups of commodities on the universal cover endowed with some memory. Of course, here you see the well-defined object here in this setting is the metric H, which does not project. Every metric which projects is like this G-Twiddle, you just, because the metric H defines a conformal class downstairs, you can pick any metric there and lift it, and this plays the role of G-Twiddle. But this metric G-Twiddle is not, it has no special meaning. H is defined by a connection. Okay, now I come to holonomy issues. So every linear connection has a holonomy. I will not explain this. I hope you know what the definition is, and so I just defined the restricted holonomy group of some Weyl connection to be this is the set of transformations obtained by parallel transform along contractible loops, piecewise small loops. Okay, so it's a subset in the holonomy, and it's in fact identity component. The connected component of the identity in this group. Okay, but this is also this group is also the same. If you look at the construction we did before, is also the same as the holonomy of M twiddle and the lift of nabla. Whenever you lift, every loop becomes contractible. So this restricted group is this. Now, in our setting, if we work only with closed Weyl structures, it means that the holonomy group of the restricted holonomy group of a closed Weyl structure is included, is contained in SO and up to conjugation. So if nabla is closed, a closed Weyl structure, because as I said, its lift to the universal cover becomes a Levi-Civita connection. Of course, all this is up to conjugation. Good. And now I will recall the Berger-Simons Theorem of holonomy. When did I start, Enrique? At 10 or 5? 8. Okay. So I have until 58. Okay, so Berger-Simons Theorem. So FMG, the any Riemannian manifold. Maybe I can put 8 here. Then there are the following 3 possibilities. Either the holonomy of the Levi-Civita connection is reducible, and this by the local Florin theorem. That's equivalent to M is locally a Riemannian product. So that's a very special feature of Riemann geometry. When the holonomy acts reducibly, then in fact you have a much stronger statement. The manifold is locally a Riemann product. This doesn't hold, for instance, for non-closed by structure or for more general linear connections. A second possibility is that nabla h of the curvature is 0, so that means MH is locally symmetric. And I can also say irreducible, because the reducible case was treated here. I will not explain what this means, but yeah, in particular, the manifold is locally homogeneous and so on, but it's a whole theory that I do not have time to explain here. And in particular, the thing which is important, MH is Einstein. So the Ricci tensor is with Ricci on 0.
Andrei, can we take a very short break? Sorry.
Sure.
Can everyone please confirm that you can see Andrei with the right laterality and not reversed?
It looks reversed.
No, for me it looks okay.
Ah,
Okay, because it's appearing upside down.
For us,
Yeah, for
it's
us it's reversed.
Yeah.
Cool. Yeah, just.
this is my left hand.
Yes.
Sorry.
Yeah, so the third case is if M is not reducible, so if nabla H is irreducible and not locally symmetric, then there is a very short list of possible holonomies. This is the so-called Berger list. So I assume that the dimension of M is n everywhere. So we have the generic case, which is SON. Then we have UN, which is corresponds to unitary matrices. This corresponds to Kähler. Special unitary group, n/2, sorry. This corresponds to Calabi-Yau manifolds. SP n/4. This is the compact symplectic group. SP n/4 SP1. P2 inside SO7 and spin 7 inside SO8. And that's it. This is the generic case. But we say that the holonomy is special if its holonomy group is strictly smaller than SON. And so from now on, we suppose the holonomy is special. So let me just point out that these three cases correspond to Kähler matrix. The matrix is Kähler here. Use this one. Oh, and this one. Yes. Okay. So and this. So the locally symmetric case is together with this here are Einstein. These are the so-called quaternionic Kähler manifolds. They have positive or negative scalar curvature or Einstein constant, and these have 0 Einstein. Well, these two are Einstein too, but I prefer to keep them with the Kähler. So now I can restate the Berger theorem in the following way, which is more convenient for us. I can say the following. Corollary. If the holonomy, the restricted holonomy of MH nabla H is special, So we don't have this case. Then either locally, either M is remaining product, H is a remaining product, Einstein, or Kähler. You see in the Berger list that these are basically the three possibilities. And now let me state our problem. So our problem, let's call this problem 1. Find all compact manifolds, compact conformal manifolds, MG, MC, with two different exact Weyl connections with special holonomy. By what I said before, this is equivalent to the following question. Find all compact conformal manifolds having two matrices in the conformal class, not homothetic because we want different exact Weyl connections. So this will be two matrices which are not homothetic, such that each of the two remaining matrices with special holonomy. So that's problem 1. That's equivalent
In the same.
in the same conformal class. Yeah. In C, not non-homothetic, with special holonomy. So from this list, you see there are basically 6 possibilities, not 9 because there is a symmetry. So both matrices could be remnant products. They could be both Einstein, both Kähler, or the factors. For instance, do you think there are 2 non-homothetic Kähler matrices in a conformal class? Can this exist? So most people think no, because they say the following: if you have 2 non-homothetic matrices in the conformal class, you have a Kähler form, omega, and e to the f omega. And they are both closed. So 0 is d omega, and it also d of e to the f omega. You differentiate, this is d f wedge omega plus d omega, which is 0, times e to the f. So if this is 0, that means that df wedge omega is 0, and then that means df is 0, so the matrices are homothetic. But here there is a subtlety. We do not assume that we assume we have 2 Kähler matrices, but not with respect to the same complex structure. And in fact, it turns out there are examples of 2 non-homothetic Kähler matrices that conformally related for different complex structures. And yeah, so let me just say the result for this case.
Sorry, Andrei,
Yes.
one question. In problem 1, the Weyl structures have to be exact?
Yes.
Yes? Okay.
Yes, exactly, because I assume I have 2 matrices with the special holonomy, right?
Okay. Thank you.
And yeah, so I want to give, before giving the result, the theorem, I give you another example, a quick short example of this situation. Let's take MI GI with I from 1 to 3 Riemannian manifolds, any Riemannian manifolds, and some function phi, a function on M2, non-constant. Let's consider the following matrix: G1 plus e to the phi G2 plus G3 on M1, which is M1 and 2 and 3. And the metric, so this is G, let's say, and G prime is e to the minus 5G, which is e to the minus 5 G1, minus 5 G1 plus G2 plus e to the minus 5 G3. Oh, no, sorry. I made a mistake here. The function has to be on the third. G2 plus e to the minus 5 G3. And this one is e to the minus 5 G2 plus G3 plus 5 here and plus. Okay. You see that we can group these metrics like that and like that. Because 5 is a function only on M2, this is a work product metric on M2 cross M3, and this is a Riemannian product. Here you have a metric which is conformal to a product metric on M1 cross M2, and a Riemannian product with another metric. So you see that we have two non-homothetic Riemannian metrics, which are both Riemannian products. And now comes the result, the theorem, which is well, it follows from a series of papers, most of them with Madani and Pika. And it says the following, the solutions to problem 1 are the following, either these triple products like before, I call these triple products. I don't have a good name for this. We can say triple worked products or something like that. Or, but here it is very important. One cannot see in my talk why, but it is very important to assume compactness. Without compactness, nothing works. And the other solutions are two conformal Kähler metrics on Calabi on the well, let's say this Calabi S2 bundles. These are so you have over polarized Hodge manifolds. So you take a Kähler manifold with Kähler class, integral Kähler class that gives you a line bundle with a positive line bundle. You take L plus C, the trivial bundle. You projectivize this. So this is C2 bundle. Complex bundle over the manifold of complex dimension 2 of rank 2, and then you projectivize this, and you get the S2 or CP1 bundle. And this CP1 bundle turns out to have two different Kähler metrics for two different complex structures on this. I don't have time to explain more details. But you see, one can characterize completely. So there are no B Einstein solutions or Kähler and Einstein and so on. And now I finish with my problem 2. Problem 2. Now let me just change here. So problem 2. I want to find compact conformal manifolds with one closed, non-exact Weyl structure, and one exact Weyl structure with special holonomy. So I assume that is equivalent to having this is equivalent to having The Weyl connection, which is exact with special holonomy, means we have a metric with special holonomy plus an exact closed Weyl structure with special holonomy. So holonomy like before. So it's a sort of generalization, but not really, because before we assumed we have two exact Weyl structures. Now we only assume one which is exact, so a Riemann metric, special holonomy, and a non-exact one. So of course we could also consider a non-closed Weyl structure with special holonomy and so on, but these questions are more difficult. I don't think we can answer them in general like we can do here. So what I would like to explain here is the solution to this problem too. When can you find a Riemannian manifold with special holonomy, which has also in the conformal class defined by the metric, a closed Weyl structure with special holonomy? So for this, I come back to what I said at the beginning. Having a closed Weyl structure means having on the universal cover. So assume this holds. So then on M twiddle, on the universal cover, we have G twiddle with special holonomy, and H, which is e to the minus f G twiddle, also with special holonomy. But we cannot reduce to problem one, because before problem one can be solved on compact manifolds. This is no longer compact. So we cannot use all the techniques we had before. So now we go through this the three possibilities, and we consider the metric H.
But you are happy for it to be non-complete.
It is always complete with respect to the lifted metric because it was compact, so complete downstairs.
Yes.
And this one is always non-complete.
It is right.
This is, as I mentioned before. But still, the Berger theorem applies because it's local. So we have three possibilities. So first, if H, the metric H, is kept, then that corresponds to the fact that M nabla is locally conformally kept. So LCK. LCK is exactly this situation. And that means that M G nabla is LCK and has, as Riemannian manifold, it has special holonomy. And that was, this was solved in one of the papers with Madani and Pilka. And then we can show after a lot of work and studying different cases, because special holonomy means, again, looking at these three cases, it's a lot of work, and we can show that necessarily MG is Vaisman. Vaisman means that theta G, the Lie form of nabla with respect to G is parallel. So nabla G, theta G is 0. And of course, every Vaisman manifold has a parallel Lie form, so it has a special holonomy because it's contained in SOM minus 1. Okay, and that's all in this case. The second case is the Einstein case. If H is Einstein, first you can notice that an Einstein manifold If the Einstein constant, if Ricci is not zero, this is impossible. Why? Because you have strict homotopy. I assume that my sorry, Ricci of H. Yes. I have strict homotheties of H. Every homotopy preserves the Levi-Civita connection, so the curvature of tensor, and so the Ricci tensor, because Ricci is obtained from the curvature by a trace not related to the metric. It's a trace which does not involve the metric. So the Ricci curvature, the Ricci tensor is preserved by the homotopy, but if you assume that Ricci H is lambda times H, where lambda is non-zero, you get immediately a contradiction because this is preserved and H is not preserved because you have a strict homotopy. So this is impossible. So then we have that Ricci H has to be zero. So if you look in the Berger list where we already removed the special Kähler and hyper-Kähler case, that means that the one possibility is that the holonomy of the metric H is G2 or C7. And now that means that nabla, the connection nabla on M is by Einstein. What means by Einstein? Well, in general, if nabla is not closed, we have to define the Ricci tensor of this, which is not always symmetric and so on. But here it's much easier. Nabla is closed on the universal cover is exact, and then by Einstein means that the metric corresponding the metric H is Einstein. So that's the automatic. But now the point is that there is a result of Todd, which I wrongly attributed to Godeschon before, but Godeschon himself told me it is Todd who did this. On every compact manifold, if you have a bi-dimensional structure, then the Lie form with respect to the Godeschon metric, I don't explain what the Godeschon metric is, but it's a uniquely defined up to rescaling metric on every manifold. Well, this is on one hand closed, but the Todd result says that it is dual to a Killing vector field. So in fact, it is nabla G parallel. It's parallel. It's parallel, and then you can immediately describe these two cases by saying that the manifold M together with the metric G is locally a product of S1 with a nearly Kähler manifold here or nearly parallel G2 manifold here. And globally, it is a mapping torus. I don't have time to explain. There is one more thing here to be said. If so, of course, every such mapping torus has special holonomy because it has a parallel direction. And but the question remains: maybe there are some other metrics because we want to characterize these couples. So this metric G is not necessarily the metric, the Godeschon metric, but we can show that it is. The only metric with special holonomy is the Godeschon metric. Somehow this follows from problem 1. And the last case, which is the most interesting one, but I only have 5 minutes, so I will speed up a little, is the case of when the metric H is reducible. Here is, of course, locally. So third case, and that would be my last slide somehow. It's the case where holonomy of H is reducible, and that is what we call LCP manifolds. So LCP means locally conformally product manifolds, like by analogy with LCK. For LCK manifolds, this metric H is Kähler. For LCP manifolds, the metric H is locally conformal. Well, here there is a very interesting result by Kurganov in 2019. Well, I don't have time to tell the full story, but at the beginning we thought such manifolds do not exist, and except for conformally flat ones or so. And then mathrm and Nikolaevsky constructed some examples, and this guy proved the following theorem. M nabla is LCP, for the moment the metric G does not appear, then and with the H is, so this has reducible holonomy, but it's not complete. We cannot apply the global Durham theorem, although this is simply connected. But the theorem says that this not only is a global Riemannian product, but one of the factors is the flat space, and the other factor is irreducible and incomplete. So on Riemannian manifolds, you can have products of no matter how many factors. But here you can only have two factors. Not only you have a Durham theorem, the Durham decomposition, which is already non-trivial, but in the Durham decomposition you have only one flat factor and one non-flat. You cannot have more. So you can already see this situation was very rigid. Next week I will give more details on this situation. And now is it simply connected? Yes, this is simply connected, but because it's not complete, you cannot apply the Durham. Only local, but this result says this is global. Yeah. And yeah, with Viviana and Adrian, we are studying since 2 years such structures on on solved manifolds, and there are many things to be said here. Let me just say one thing. So among these manifolds, so assume now that let now G be a metric on M on such a manifold, and with Lie form theta G and the lift theta G twiddle. So we define G to be adapted to the LCP structure if theta G twiddle, when we lift the form, vanishes on restricted to RQ is 0. So that's equivalent because remember this is d of some function phi. It's equivalent to saying that phi in fact is a function of the second factor. Is the pullback by the projection of the function. And then there is a proposition by Brice Flamencourt in 2021 that there exist adaptive metrics on LCP manifolds. Later on, we proved with Kähler that the reducible metric is always adaptive. But anyway, and why am I insisting on this? So I'm almost done. When you have an adaptive metric, you have a possibility of constructing more LCP structures from a given one. So you take any MG LCP like that, and you make a product with M prime G prime. I claim that this is again LCP. How to see this? We look at the universal cover, M twiddle times M prime twiddle. We have the metric H, which is e to the minus phi G twiddle, which is GRQ times plus GN. Remember, it's a Riemannian product. And now let's look here. I just take the Riemannian product. So yeah, G prime. So now if we look at the metric e to the minus phi G twiddle plus G prime twiddle, this is a bit like for the triple product. You see, it's E minus phi is GRU plus GN plus E to the minus phi G dot prime. And these two, that's a work product because phi only depends on N, not on Q. That's the point. And so it's a work product. We still have this factor. We still have the phi one of the product is the product of the phi one of this product is the product of the phi ones. And it acts by homodities with respect to this, or even isometries if we take only people from here. It's co-compact, so on. So we have, and the thing is that this is again LCP, just by this being LCP, then this is LCP, and of course it's reducible. And now the theorem, and I will finish with this, with Belgun and Flamencourt and myself from last year. It says that LCP manifold. So if we have nabla is LCP and MG has special holonomy, then this manifold cannot be Einstein and cannot be Kähler. It can only be a product, and the product is exactly of this type. And this is actually the most difficult part. It's not at all trivial. So, because when you have this LCP manifold and a metric with a reducible holonomy, this doesn't tell you that you're in this situation. You still have to, you have a locally autonomous product, you have parallel distributions, but you have to see how they are, they behave with respect to this other decomposition. So there are maybe things that we can discuss. Thank you very much for your attention. I'm done.
And the perfect timing. Adrian, have I got any online questions?
Not yet.
So in that case, I'll ask one absolutely ridiculous question. So I can think of a problem 3 and a problem 4, and then hopefully you can tell me why they're completely ludicrous, right? So here's a problem 3. Let's make both of them closed but not exact.
Yeah, we have no clue about that yet. It's
apparently,
yeah, it is.
I thought it was obstructed by some smart reason.
No. It's perfectly possible, but we don't have many how many ways to attack this.
You want to anchor one of them to be exact, so that you have.
Yeah. We have because we have a Riemannian metric on a compact manifold. That's important. If you only have 2 Riemannian metrics on a non-compact manifold, it's because here I didn't tell you the details, but you integrate a lot on the manifold. You use Stokes' theorem at the time. And, if you don't have a metric downstairs, you're a bit lost.
Okay. Adrian, did you get a question?
No.
So here's a problem 4. So supposing, so fix one of them to be exact, because I understand this is important.
And the other one?
The other one is a prescribed 2-4. Instead of just calling it closed, I now set up a PDE with the prescribed condition. I give you a 2-4 and I ask, can I arrange for the theta to be this particular form?
That means the non-closed case, because a non-closed Weyl connection has the so-called the Weyl curvature is given by the Faraday 2 form. So whenever you have
I fix a Faraday 2 form.
Yeah. This case is also quite difficult. We have very small parts of it solved.
But it's not trivial.
No, it's not stupid.
Oh, okay.
No, there are no stupid questions anyway. But I have very functional results on this, and I didn't thought it was worth mentioning that yet.
Okay. All right. Cheers.
Any more questions from the online audience? From the
No, no.
in-person audience?